Hello, y'all. How are you doing? If you're watching, be sure to drop a line, make a comment on the live chat, or if you're watching later, be sure to drop me a line in the regular comments for the video. I'm trying a slightly different setup with my audio, mic and setup and everything to see if I can keep my uh, volume pretty level. Seems like it's looking good at the moment. So be sure to let me know in the comments or the live chat how it's going with the volume, if I need to be louder or lower, smoother or what have you. And what we'll be doing today, as the video showed, is looking at some electromagnetics. I'll be reading through one of my textbooks for my class this semester, starting in chapter 3. So we sort of went through chapter 2 already. And chapter 1, I guess technically we didn't do chapter 1. But in the future, I may come back and do the previous chapters. I started reading through the earlier ones on my own, and went through the concepts in the second one, but it's mostly a repeat, thankfully. I did some studying earlier in this review of things from previous classes, which I had to spend some time learning. But chapter 3 is mainly the new stuff. So, and that's the homework this week. So we started on chapter 3. This will be the general size of the text. Notice my pad is turned vertically at the moment, so we'll see how that works. And actually, let me change my lighting situation here. I just realized when I started that the light I don't prefer being on is on. One moment. Right. We'll go ahead and get started. I'll be reading through the book. I'll be making notes as I go. This is a indication of the size of the text, the size of how the text will be as I go along, and we'll see how this goes. So we're in EM, Pollock, and Stump. This is chapter 3. And it's called Basic Principles of Electrostatics. So the theory of electromagnetism encompasses all electric, magnetic, and optical phenomena. So EM, electric, magnetic, and optical. All of these fall under EM. To learn such a far-reaching theory, we must start someplace. We start with electrostatics, which is conceptually the simplest part of the full theory. Many of the theoretical ideas and mathematical techniques that we will acquire in studying electrostatics will be used again in the other parts of the theory. Everybody who comes to this subject has already had a lot of experience with electricity and magnetism, both from applications such as electric lights, motors, telephones, radio, and television, as well as from natural phenomena such as light, lightning, static discharges, and Earth's magnetic field. Often the motivation for studying electromagnetism is a desire to understand the physics underlying these experiences. It is therefore natural to expect a book on electromagnetism to start with discussions of such familiar devices and phenomena. However, these discussions must be postponed until later. We must start with electrostatics to lay the foundation for later understanding of these more complicated things. So on the EM is founded on electrostatics. Devices are made by people, so it's fair to say that they're understood. But some natural phenomena are only partly understood and remain the subject of current research. Electrostatics is the science of the interaction between electric charges and the electric field in static systems. So let's define electrostatics. Electrostatics, the science of the interaction between electric charge and electric fields in static systems, systems that do not change in time. So ds df over dt equals 0, no change in time. Strictly, the charges must be at rest. So Q at rest, fields must be constant, E, B, constant. Practically, we also use the equations of electrostatics for systems that change slowly in time, a rather forgiving approximation called the quasi-static approximation. As we will see, this approximation permits us to apply electrostatic principles to many electromagnetic devices and phenomena. So 3.1 Coulomb's law. All of electrostatics can be derived from two principles, Coulomb's law and superposition. It's interesting. So electrostatics deals with Coulomb's law and superposition of fields. Well, they didn't say fields, but superposition. Coulomb's law, which is a formula for the force between two point-like charges, is based directly on the experiment. So what's the word for that? Something that's based on experiment. There's a fancy word. Empirical. And hold tight. Well, a moment, I'll play some music while I get some water. I'm over here. Right. So Coulomb's law, based upon it's empirical, based upon experiment. The first accurate and detailed measurement of the force between charges were made by Coulomb in 1785. From these experiments with a very precise torsion balance, Coulomb discovered that the force is inversely proportional to the square of the distance and in the direction of the line joining the charges. Also, the force is proportional to the product of the charges. Writing an equation that expresses these facts, the force on charge Q due to a charge Q2 is, so this is Coulomb's law, F equals KE Q1 Q2 over R squared, and R hat is the direction, which is in line between the charges, where R is the distance between the two charges, R hat is the unit vector pointing from Q2 to Q1. So R hat is Q2 to Q1. We let R be the vector from Q2 to Q1, then R equals the magnitude of R, and R hat equals R over the magnitude of R. So we have Q1, Q2, this would be R, the distance, and if I make a coordinate system here, make this a different color. This one vector, this is the second vector. Trying to tap the line, but it wouldn't budge. So this is R, and it's going from Q2 to Q1. So if I have the line going this way, this would have to be Q2. This would have to be Q1. I guess I could go ahead and call this R hat. So R, let me see here. So that would be R. R equals Q2 Q2, at least Q2 to Q1. I believe I'll write this way. So looking at it in vector form, this would be Q1 minus Q2 equals R hat. So Q1 is going right here. Q2 is going here, so I'll put that at the end, the opposite direction. And that will give me R hat, right? And if we want the R hat, not the vector, that'll be the vector R divided by the magnitude of R, or R hat, use R arrow divided by R. So that's going to be Q. I'll do this as a 2 by 2 vector. We have X and Y. So this will be Q1 X minus Q2 X, Q1 Y minus Q2 Y. All right. And this would be our R and the magnitude of that vector. be this. Looks like they're doing this in a less cumbersome notation, but that's what the value would be. So that simply equals Q2, or I should say, let me go back here and make these X's. To match the notation in the book. But we understand that it's the vector going to where the Q is. Right. So that equals x1 x2 over the magnitude of x1 minus x2. That's r hat. So we put all this together. This will be F equals K Q1 Q2 over, and r squared would be x1 minus x2 So, okay, so they're really putting the magnitude squared. The magnitude of that squared, even though the magnitude squared does equal the x squared minus y squared, um, it allows us to put it in a different form by doing it that way. Thinking about we'll take the magnitude squared. Magnitude squared will be this without the brackets. Then the magnitude will still be this with the square root. So that will essentially be um, times 1 plus 1 will be 3 over 2. That's essentially what that'll be when you multiply this by the r hat without doing the square thing separately. So this is x1 minus x2 over magnitude of x1 minus x2. Trying to see how we get the notation from squaring it. Two squared magnitude. So the magnitude has the square root on it. Okay. So this is the same thing as and the square root of that is the magnitude. Nope, actually I wrote that wrong. It'll be 3, 2. I have x1, 3. That equals, or x2, 3. That equals third. It was that way, but I guess it doesn't really matter. Like if I put this on the inside of here, shouldn't matter either way. See, is this the same thing as the square root of x cubed squared? So this one is x3 x times x square root. So that should equal square root x square root x square root x. It's the same thing as cube root square. That was 2. Let's see what the square root of 2 times the square root of 2 times the square root of 2 is. The square root of 8. Yes, it does give the same thing. So if you do the square root first and multiply after, or if you multiply first and square root after it, it's the same. So that is the same thing as squaring this whole thing. It should be the same thing. So this has a 2 there, 3 on the inside. Wait, hold up. I think that's the same as squaring the inside. If I have 2 squared, and then I take that to the cube root, that's different. So it's not here, it has to be on the outside. Same thing here, this would have to be on the outside. And it does match, as long as it's on the outside. And that begs the question, how does that work so well? Do 2 to the cube root. Now square that. Okay, I think there's an easier way to do this. Starting from here. So we know that's correct. We have this is to the 2/2 power, and the square root is to the 1/2 power. So that is to the 3/2 power. So we can also say, since those are both exponents, we can say this is 1/2, and then we can cube the outside. So this becomes the magnitude of x1 minus x2 cubed. Just from working with the exponents themselves rather than the square root. So this must be the same process. So this does mean, similar to what I had it before, the cube has to go on the outside. Either the cube has to go on the outside and the 1/2 within, or the 1/2 on the outside and the cube within. Either one of those will work. So these, given the location that they're at, are interchangeable. And it'll give us the same thing. So technically that will be the square root of x1 minus x2 cubed equals x1 minus x2 cubed and the square root of all of that. Okay, so let's try this. Square root of 2 cubed and root 2 cubed. So that does give me the same thing. All right. So it has to be all the way on the outside and around the inside part, and then it works. And that works. All right, so we have that worked out. So now we know that this works. So we have f equals K Q1 Q2 over magnitude of x2 minus x1 cubed and x1 minus x2 on the side. And this is what they call equation 3.2, right? So that is Coulomb's law with vectors. And this would be 3.1. And this is the complicated way that we get to R hat, by the way. If anybody from one of my classes that I'm a learning assistant for happens to watch, in the previous semester, I worked out how to calculate the R hat. This is actually a simpler way, I mean, a more direct way of terming it. What it is, what I ended up doing, now that I look at it now, all you're doing is just treating everything as a vector very directly, and then calculating the magnitude, or rather the magnitude of the distances between the two charges as vectors. So let me see, by the way, keep in mind you could join Discord live, ask questions live. Looks like nobody's in at the moment. The link is scrolling at the top of the screen. If anybody joins and want to join the live. Right, so we have that. Constant of proportion, and that's I skip some reading. Where R is the distance between the charges, R hat is the unit vector pointing from charge to charge. And if we let R hat be the vector from Q2 to Q1, I thought they said Q1 to Q2. I know it doesn't matter, but I want to see if they're keeping a very consistent verbiage. Right, well, R is the distance between the charges. R hat is the vector pointing from Q2 to Q1. Okay, that's right. So going from Q2 to Q1. So that's how we got Q1 minus Q2. If we let R be the vector from Q2 to Q1, then R equals the magnitude of R vector, and R hat is R vector over R. For Q1 and Q2 with the same sign, the force is repulsive in the direction of R hat. The charge is of opposite sign, the force is attractive. And R hat would simply be a vector along this line, but that's only 1 unit long. So the magnitude of R hat equals 1. It is useful to introduce another notation for the force equation that displays explicitly the two positions. Let x1 and x2 denote the positions of q1 and q2 with respect to some origin in space. So that's what we did here. I'll call this my figure 1. As shown in figure 3.1, or they do have a figure coming up, I guess it's on the next page. Then the relative vector r from q2 to q1 is r equals x2 minus x1, and the force on q is what we have here. Force equals k q1 q2. And that's well, it's not the greatest simplification. This is the best simplification, and I guess they basically did one more thing to it, and it said k q1 q2 and put those on their own. And then we have x minus x1 minus x2 over the magnitude of x2 x1 minus x2 cubed, right? And this is the actual 3.2 after they simplified it a bit. So it makes sense? The constant of proportionality k depends on the system of units. In this book, we use standard SI units, also known as rationalized MKSA units for meter, kilogram, second, ampere. The table below lists the units of some important quantities. And you have meters, kilograms, seconds, current is in amperes, force is in newtons, charge is in coulombs, potential is in volts, and magnetic field is in teslas. And K in this equation equals 1 over 4 pi epsilon naught, or I'll skip the middle version and say 8.99 10 to the 9 newtons meters squared over coulomb squared. And that's the value I'm used to working with. And epsilon naught is the permittivity of vacuum or permittivity of space. You're going to charge coulomb, so 1 coulomb equals 1 amp times second, where the unit of current, ampere, is the fundamental electric unit. The ampere is defined in terms of the magnetic force between current carrying wires. As we'll learn in chapter 8, the coulomb is defined such that 1 over 4 pi epsilon naught has the value in 3.3. I see. So if you want to know what epsilon naught is, 1 over 4 pi epsilon naught equals 8.99 times 10 to the 9 newtons meters squared over coulomb squared. So 1 over 4 pi 8.99 10 to the 9 newtons meters squared over coulomb squared equals epsilon naught, which makes sense. But when we put that in for epsilon naught, everything else cancels but the 8.99. Right, so that must be correct when we actually calculate that value. Then when we get that value, we put that whole thing in for epsilon naught, and then it balances or averages out. So that works. So the fact that everything cancels out when we put it in symbolically, like the symbols, means that if we actually put the value in for that and then multiply everything out, it'll give us the same thing back. And they put a drawing in the textbook, which is, pretty much my drawing. These are vectors. And if I was to put the vector symbol where they put it in by there, it's pretty much what their drawing was. This is the origin. And if we have two charges, two positive charges, then the force is going in opposite directions. Coulomb is defined such that, uh, right? Interesting. Maybe one day I'll need to plug in the units for that. I guess technically, epsilon naught, the units of it would have to be Coulomb squared over Newton's meter squared in order for that to work out. At least, yeah, Coulomb squared over Newton meter squared. And then that will flip back up. Everything is looking good so far. The numerical value of the force in newtons between two charges, each of 1 coulomb, that are 1 meter apart. So the numerical value of a coulomb is the force in newtons between two charges, each of 1 coulomb, that are 1 meter apart. And now I believe we define the meter with the speed of light. Remember that, right? Coulomb's law 3.1, the first principle of electrostatics, is an experimental fact. So this is an experimental fact. Right? Let's go to 3.11. Check something really fast. Right? So 3.1 is the superposition principle. Pretty short little section. At least 3.11, that is, like a subsection. Superposition principle merely states that a force on a charge Q due to a set of charges is the sum of the individual Coulomb forces. So they have it written thus: F net equals the sum, K equals, and I'll say I equals 1. So however many there are, Q, Qi, where Q is the charge that we want the values for. And I'll just call that K. X minus Xi over the magnitude of X minus Xi cubed. Right? So what this ends up being is we rewrite this equation over and over again with each uh, different charge xi, and it becomes a sum of n number of components, where x is the position of q and xi is the position of qi. So now we're in 3.2, the electric field. So 3.2.1. Right, so we have a definition here. We have the electric field, Ex, is a vector valued function. Vector valued function, f of x. That is, there is a field vector at every point in space. The definition of Ex is the force per unit charge. The force per unit charge. So the force per unit charge is this force per unit charge that will be exerted on a small test charge, Q, if it were located at X, in the limit as Q approaches 0. I'm not sure why Q would approach 0, but I'm sure that's not so necessary at the moment. This test charge is taken to be small so that it does not affect the other charges. Because the force F on Q is proportional to Q, the electric field is independent of the test charge. So Q is a test charge, and which has a unit charge. So the force that would be on that test charge, that's what they call in the electric field. The definition provides a technique and principle for measuring the defined quantity X. Take a small charge to X and measure F divided by Q. So you measure the force divided by Q, the one that you measure the force with, and then you get the electric field. The subject of this chapter is the interaction between charges and the field. The definition 3.5 tells us one aspect of the interaction. The electric field exerts a force on the charged particle Q, given by F Q equals Q E X, where X is the position of Q, and Q is the test charge. The equation states how the field affects the charge. Next, we describe the other aspect of the interaction, how charges affect the field. So again, the All right, so Q is a test charge. Multiplying the electric field by the test charge is how much force is on the test charge. Dividing the force you get by the value of the test charge tells us the value of the electric field at that point where Q was. Right? So charges as a source of electric fields. We regard the electric field as a real physical entity, not just a mathematical construction. From the way it is defined above, one might think E is just a mathematical technique for describing the electric force, but that is the wrong way to think of it. We know that light consists of fluctuating electric and magnetic fields, and no one would dispute the statement that light is a real physical entity, not just a mathematical construction. Field theory was developed by Faraday and Maxwell as an alternative to action at a distance, right? So Faraday and Maxwell developed the field theory instead of action at a distance. So now there's not some charge magically affecting something a distance away. It is literally you reaching out and touching it with a field. The field is something real that extends throughout a volume of space and exerts force on charges in that space. Now the question is, where does this entity, the field, come from? What is its source? Electric charge is one source of electric field. In electrostatics, charge is the only source. So in electrostatics, the only source is electric fields. In chapter 10, we'll learn that another source of E is a magnetic field that changes with time. So a change in magnetic field also creates an electric field. But that's a dynamic rather than a static phenomenon. So charges are static. It just is. There's no uh, change in the charge over time, but a changing magnetic field is dynamic because it changes with time. So let me see. That's why they call it electrostatics, because the charge itself, the value of its charge, or what have you, does not change with time. Let's continue with this. Comparing equations 3.5 and 3.4 shows immediately that the field created by a set of static point charges is so basically what they're doing there is they're taking this equation here, 3.4, and they're simply removing the charge where we're getting the force at, and thus that gives us the electric field. And they're calling this 3.7. Right? So you add up all the QIs, you get the electric field at that point. At a, long as all the different QIs, we're getting the radius to that point in space and the direction to that point in space, that same point from wherever they're at. We refer to X as the field. Now, one interesting thing that comes to mind, even if you have two charges that are at different locations, like let's say on different parts of the Earth, you can still get the superposition of their charge on a point as long as you get the calculation with the precise magnitude and direction to the point that you wanted at relative to the two charges. So I can want the field from right here, and I can have my two charges there, or I can have my one charge will over here, but simply calculate what the field would be there and calculate what it will be there when I add them together. That'd be equivalent to calculating, what it is like that, as long as I get my direction and distance correct. The direction has to be correct. The distance has to be correct. We refer to X as the field point and to the XKs as source points. So the X where we're going is the field point, and all the X's pointed to that point is the source point. I think field point was it's not a good word to use. The vector X minus XK over X minus XK is the unit vector. This makes sense because you have X over the magnitude of X, which is R, the unit vector, and then divide it still by R squared, which is the magnitude of X minus XI squared. And the unit vector is in the direction from the source point towards the field point. The field as a function of X due to a single point charge at position XQ is E equals Q I K, but it is writing the single one here. E of X equals Q K X1 minus X, or X. Then breaking this apart, X minus XI over magnitude of X minus XI, and then 1 over magnitude of X minus XI squared is going to equal QK x hat uh, all over r squared, which is the magnitude of x minus xi squared. So this is equation 3.8. And technically this is r hat. All right. R equals q minus, excuse me, r equals x minus xq. That's the distance between the 2 points. The point where the test charge is and the point where the field is coming from. Charge acting as a source of E is the other aspect of the interaction between charges and the electric field. Equation 3.8 states how a charge affects the field, and 3.6 states how the field affects the charge. So the field affects the charge by making a force, and the charge affects the field. I'm not seeing how 3.8 shows how the charge affects the field. So another field affects the charge by making a point charge. I guess a charge affects the field by making the field. I don't think that was worded well. Maybe they were just trying to be cute right there. Example 1, figure 3.2 shows 6 identical charges, one at each vertex of a rectangular hexagon in the xy plane centered at the origin. What is the electric field at any point x in the xy plane? Let the charges be numbered with the index k from 1 through 6. And the position of the k charge is xk equals I cosine. Ooh, that's ugly. The field for arbitrary x is then obtained from 3.7. It is doing some weird uh, notation, but essentially it's the same thing. The same equation that I have here, but of course they have to be complicated. The field is singular, i.e. goes to infinity at the 6 charges, but it's finite everywhere else. See what they mean by goes at infinity at the 6 charges, but it's finite everywhere else. What is the field on the x-axis? Set y equals 0 and obtain, oh, I see. It is clear that x0 must be 0. To be x0 must be 0 because of the symmetric position of the charges. Sum in 312 the terms with k equals 3 and 6 are 0. and other terms cancel in pairs. At the origin, E is 0, which is easily seen from the equations, or just physically because the fields due to charges on opposite vertices cancel. And an example of asymmetric approximation, what is the field on the x-axis far from the origin? Accurate to an order of x to the negative 4. The y component is 0 on the x-axis. For x much greater than a, the x component must be calculated by expanding 3.11, which is the x version of the equation. In a power series in a small quantity a over x using the method of Taylor series. The result, equation 3.13, the leading term is as expected the same for a point charge 6q at the origin. If the 6th charge is removed from the group, what is the field at the origin for the remaining 5 charges? We can start from 311, but sum only the k1 through 5. However, the superposition principle enables us to answer the question more easily if we realize that the fields of charges 1 through 5 is the same as the field of charges 1 to 6 superposed on the field of a charge q, negative q, at a 0. The field at the origin due to the 6th charge is a 0, so the field of charges 1 to 5 is, note the sign, all right? We'll go ahead and work through this, and then I'll go ahead and call it a night. So give me a moment here. Some image of the Eagle Nebula, I believe it's called, M16. While I get a hold of this image from the book. And I'll use the actual one that they have. When I first saw this problem, I was thinking, how they do it when they're not giving me any numbers, but suppose they literally want the symbolic representation of it. Right. So this is the problem we're going to work here. So we're going to find the electric field along the y-axis, the electric field along the z-axis. So E equals K Q, and we have x1 minus x2 over magnitude of x1 minus x2 cubed. And for the y direction, if I take this as my angle, EY equals KQ x1 minus x2 over magnitude of x1 minus x2 cubed sine of theta. It is some complicated thing to get the position of everything. A cosine a power over 3, but I don't think it's necessary to figure that out. Is it to be so technical? So if that's theta, we know that Q1, let's just say Q6, is at A cosine theta, which is at A. But that still doesn't, well, A cosine theta I. Oh, I see what they're doing. It is making a circle. So a circle is x squared plus y squared equals r squared. That's the magnitude. Circle x cosine theta plus y sine theta equals c. If I remember right. That'd be the position. It's not necessary to do all that. So position along the y-axis, E1 equals now you see that each half is broken up into 3. So we know that theta here is going to be 180 divided by 3, or 60 degrees. That's where that point is at. So we could get the x coordinates of everything. Or you can say that the position, this vector here, so now we're getting somewhere, x1, the vector x1 is going to be a cosine theta plus a sine theta. And that's simply just using basic trig. X2 is the same thing, equals, actually we can say x1 equals a cosine theta I. Oh, maybe I is a bad letter to use in this context. I'll say theta n I plus a sine theta n j. And theta n equals 60 n. So for theta 1, theta is 60. For theta 2, theta is 120. For theta 3, theta is 180, and so forth. So that's going to be our vector for position. And if we're going along the y-axis, we can say x2, which is the field point, is going to be 0 I plus good letter to use here, plus j, not. So along the y-axis, it's going to be 0, an infinite number of points. So that means that y equals, say, the constant, q I, let's just say xn, and I'll use n's, equals the sum of, so let's work one at a time. E1 equals k q1 minus, I should say k q1, yep. And then we have the unit vector x1 minus x over the magnitude of x1 minus x. That'll give us a direction. And then 1 over x1 minus x. Give us the distance. So call this x f for the field point, right? And this will be the same for every single e. So it's E1Y. So EY equals the sum I equals 1 to 6 of K QI X XI minus X F. That's the distance, the distance between them divided by X I minus X F. That's the magnitude of that distance. So we have the direction of one unit going directly to that point, and 1 over the magnitude of x1 or xi minus xf squared. The magnitude of the electric field along the y-axis. So if J is 0, if J equals 0, then xf equals 0, 0. So, oh, and I forgot my sign. EY would be sine theta, only the part that's going up. Sine theta I, actually. So the theta is going to change for each one. So y equals 0, or I guess I should say if j equals 0, then xf equals 0. So sine of theta 1 equals sine of theta equals negative sine of theta 2. Give me negative sine of theta 5. So sine of theta odd. It's a good way to write this. Sine of theta 1 sine of theta 1 3 5 equals negative sine of theta 2 6 4 respectively, because sine of 30 and sine of 50 got the wrong ones. sine of 30 and sine of negative 30. Opposite. So at 1 will be sine of 30. One is opposite. One, let me step my numbers. It's top to bottom. So sine of theta 1, 2, 3 equals negative sine of theta 5, 4, and 3. They're 5, 4, and 6. Respectively. And QI equals QJ, that the origin is 0. And as we get farther along, it will combine above the x-axis, and above all the points. They all contribute. So if J is greater than A, then sine of theta I is always positive, and all charges contribute to E, right? And the electric field along Z is going to be interesting. It's like I touched my mute momentarily. Hopefully, I just saw the light go off, so I'm sure it wasn't. So with the Z-axis, the same equation holds, except that EZ equals KQ1 is going to be X1 minus XF along the Z-axis. And like I need to draw this. So we have this. I move the charge over, at least the point over a bit. Oh, froze. Happens sometimes when it's saving. Right. So let me go ahead and draw this. We have trying to save for a while. We have this coming down vertically, and to the right, let's say. This is one of my charges. This is one of my charges. Uh, this is a right angle. And now I'll call this theta. And this is my point. And this is this will be the XY plane. And this would be the Z axis. Right. So essentially all the XY plane values cancel. So we only need cosine. And I'll actually call this phi instead, since theta was up there. All we need is cosine of phi for the vertical. And all the angles should actually be the same, so this should be easier. Right? So we're going to be all of these, x minus xp, and p equals 0 and z right there. I'm going to add all of these up, and yeah, that'll be it. And technically, since all of them will be the same, I can actually say EZ equals 6 times Q, any Q if they're all the same, x minus xp, and cosine of all of them will be exactly the same since it's symmetrical. And only the y value counts. They all will be the same distance from the point along the z-axis. So we could just look at the y component and leave it at that. And p equals 0 z. And that'll be the same for any point along the axis. And actually, this should probably be xp minus x, because p will be v is greater than or equal to 0. and x equals x, y. And x, y are greater than or equal to 0. So this will ensure that we always get a positive value without having to put a negative sign in the front. It'll always be going up in a positive direction, and x will be, v will be greater than or equal to 0. So if z is 0, see if I could think of a simpler way to do this. All of them are going to be the same. The y, the z component doesn't cancel but only adds. So we can say x equals a 0. If z is 0, cosine of so we're trying to consider when it's in the turn of the axis. It'll be like when p is in the 0 of the axis. Okay. So if z is 0, p will be 0, 0. But x will still be a 0. And that will be negative. So that's not correct. You have to add them up because if it's 0, then they will cancel out. So this only works if z is actually greater than 0. As long as z is greater than 0, well, it works. Because uh, if p equals 0, 0, then theta, then phi equals 90 degrees, and cosine of phi 90 equals 0. So yes, it does work. The angle will take care of it. and E equals 0. That's they all cancel. So Z is greater than or equal to 0. Theta will take care of the um, Y component, which would be 0 when they're on the line. So this equation does work. Just take 6 times that, and it will compound and add as we get farther away. Right. So I think it's a good place to stop. I'll leave it at this. And you can look for me again next week. And I'll probably continue with some quantum on Friday and some EM on Saturday. So I'll see if I can keep that progress going. So thank you all for joining. Those who join later, make sure you like and subscribe. Keep in mind, I do have tutoring. So if you'd like some tutoring in math, science, uh, including physics, astronomy, some chemistry, chemistry 1 and 2, let me know. I work as a learning assistant. So, and I worked as a tutor before that professionally at the college, university level. So I can help you with anything up to uh, sophomore, junior level math and science. So you can check me out at darrelleweberjr.com, website at the top of the stream there. I'll see you all next time.